Okay, so let me introduce our next speaker, Professor Waldemar Hołubowski from Silesian University of Technology, and the title of his talk is Similarities and Differences between the Group and Lie Algebra of Column-Finite Infinite Matrices. Please.
I would like to thank the organizer. I'm proud that I am a second time in Sumy. I was at the previous conference, Algebraic conference in Ukraine at Sumy. I have a very good remembrance from this conference. Now I am in contact form. I hope that the third time in Sumy, it will be also not online, but in contact form. I will talk about groups and Lie groups. I will start with some picture. If we have a general linear group of n by n matrices over a complex number, and we look at ideals of this Lie algebra, we know that there is a nice picture of such form, where here we have zero ideal in this Lie algebra of n by n matrices. Here we have a scalar matrices which form a center, and here we have a special linear Lie algebra of n by n matrices. So these are matrices with trace 0, and so in this Lie algebra we have 4 ideals. Similar situation is if we look at a general linear group of n by n matrices over a field. We let L is greater or equal to 3, K any field. And if we look at normal subgroups which corresponds to ideals in Lie algebra, we will see that we have the greater ideal which coincide with general linear group. And here we have also such a square. Below we have identity of group. Here we have the group of scalar matrices, which for the center of this group. And here we have a special linear group of matrices with determinant 1. And what is here we have a very, very old result of Jordan, who says that if we have a normal subgroup H in a general linear group of such kind, which is not contained in the center, so H is not contained in the center of this group, then this normal subgroup must contain a special linear group. And situation is here something different, because here we have a thin line, usually if K is a field of characteristic 0, and here we have a thick line because we have many normal subgroups of general linear group, which are subgroups of scalar matrices. Analogously, we have here many normal subgroups which contain special linear group and are normal subgroups in general linear group. And how to generalize these observations? So we look at a vector space. Let V be a vector space. I will restrict to vector spaces over a field K. And usually we look at a dimension of V. In many cases, we assume that the dimension is finite, but we are interested in dimension of V, which is infinite. And so we start with the following. Let a dimension of V be a cardinal number Aleph delta. And if we look at cardinals, we have the following. If on infinite cardinals, we have Aleph 0. Aleph 0 is less than Aleph 1. less than, here we have Aleph alpha, and here we have Aleph delta. Aleph delta is cardinality of dimension of any Hamel basis of V. And there is a very known problem which was solved by Jacobson. If we look at endomorphism of this vector space, the problem is how one can describe all ideals of this algebra of endomorphism. Here we have linear transformations from V to V, and we look at two-sided ideals. And the answer of Jacobson was as follows. We denote by F alpha the set of all endomorphism F of endomorphism of V such that image dimension of image F of V has cardinality less than Aleph alpha. And we obtain the following situation. We have a 0 ideal, we have F sub 0, F sub 1, here we have F sub alpha, F sub delta, and here we have endomorphism of V. And the answer, the Jacobson proved that all two-sided ideals are in this sequence. So we have an ideal which is connected at 0 is ideal of all linear functions which have finite images, and F delta here is ideal of all linear transformations such the image of the range of this transformation is less than Aleph delta. And here we can say that these ideals are linearly ordered. And next, we look for next result. And in 1958, Alex Rosenberg proved in study the following situation. We look at all linear transformations which are invertible, so it corresponds to the group, general linear group of linear transformation of vector space V. And he tried to answer the question, what are the normal subgroups of this general linear group? And the answer was as follows. Here we have a general linear group of linear transformation. Here we have such a picture, which is like a ladder. And here we have something between this ladder. And what is the answer? We say here is a subgroup G0, and G0 is a subgroup which is formed from all linear transformation of the form identity plus some matrix A, which A belongs to F0. G1, correspondingly, these are all linear transformations which have form identity plus some other linear transformation which belongs to F1, etc. So here we have G delta, the last on this part of this ladder, and here we have a direct product, a direct sum of scalar matrices which form a center of this group, direct product with G0. Here we have a direct product of scalar matrices times G1. Here we have G alpha, direct product DSC times G alpha. And here we have direct product of scalar matrices times G delta. And the answer of Rosenberg was such that above the G0, these are the only normal subgroups of GLV. The problem was what is below G0. I studied earlier groups of column-finite matrices indexed by positive integers, and after some time I look at Lie algebra of such column-finite matrices. So we have algebra of column-finite matrices over a field F, K, and we use a Lie bracket. AB is equal to A B minus BA, and I study the situation, what the problem, which how to describe ideals in this Lie algebra L column-finite infinity K with this Lie bracket usual AB minus BA. And in my joint paper with my former PhD student, Sebastian Żurek, we find the exact answer. And the situation here is much complicated than here in this upper part, if we consider general linear groups, for example, and I will say about it later. And what is the answer? We have GL, general linear group of infinite and by infinite matrices indexed by positive integer over K. This is a group of column-finite matrices. Here we have the following picture, and this picture will be sorry, we have a general linear, we consider algebra of general linear column-finite infinite matrices, and what we can say about ideals. The first ideal, which is maximal, is the following: scalar matrices plus GL finitary. GL finitary corresponds to the algebra of F0, so it contains all matrices of the form of such kind. We have some rows, non-zero rows, and all other rows are zero. And we have the natural ideals, and here we have GL fin. So these are matrices of such kind. So as linear transformation, we have a dimension of image is finite. And here we have below SL fin. So we have such matrices with trace 0 in left upper corner, where you have non-zero coefficients. Here something, and here we have a trace equal to 0 and 0, 0 below. And here we have scalar matrices plus a special linear finitary, linear algebra, and of course we have the following. Here we have a zero ideal, and here we have a scalar matrices. And the problem was how to describe ideal which are in this square. And the answer is that these ideals, in fact, are in the same level as here we have a scalar matrices plus a special linear. Here we have GL fin, and here we have scalar matrices plus GL. And here we have SL fin. And all such ideas, we see that, for example, as Lie algebra, here we have a quotient algebra GL fin over SL fin is one-dimensional. The same is also true here. And here we have a finitary extension of finitary general linear algebra by a scalar matrices. And here we have some ideals JK, which are also one-dimensional extension of special linear finitary algebra. So this picture is in fact is not simple. However, the description of idea is very, very simple. And now, what we can say about extension of this result, this was done for incountable case when we have a vector space of countable dimensionality. We can look at such column-finite matrices as and look at such Lie algebra. And in fact, to describe these ideals JK, we used a generator of this Lie algebra over SL fin and generator of this Lie algebra over special linear algebra. And next we take a linear combination, and this linear combination is parameterized by two parameters, but we can exclude one, and we obtain ideals in such a quantity with each. We have these ideals the same number as the number of elements in a field K. So what happened next? The next step was our joint paper with Oksana Bezuszczak and Bogdana Olejnik. And we consider the situation of Lie algebra GL-V of any vector space with a dimension of V equal Aleph delta. And what we can say about the situation in this case, this result appeared in a proceedings IMS in this year, and the picture is similar to the picture which was shown earlier. We have here GLV, here we have GL delta, here we have such infinite ladder, infinite or finite ladder. Here we have GL0, GL0 plus scalar matrices DSC. And here we have GL1, scalar matrices plus GL1. I mentioned here that GL0 is exactly the Lie algebra of all linear transformation which have which images ranges of such transformation are finite. And what we can say about this ladder is very, very similar to the case of general linear group. However, we can extend this graph of ideals. Here we have the situation described earlier. Not in general cases, we have also such kind of ideals, they say, which are one-dimensional over SL0. And here we have scalar matrices plus SL0, scalar matrices, and here we have ideal 0. And this result was obtained after the proving the result in a countable case. Looking at this result, I and my PhD student, former Sebastian Żurek and Martyna Maciaszczyk, we look at situation and what about a general linear group of infinite column-finite matrices over a field K. So we try to look at normal subgroups, H, a normal subgroup here, and situation is as follows. We have a general linear group of column-finite matrices. We have a group of finitary matrices, GL0. Here we have a scalar matrices plus GL SL0, matrices which differ from the identity in finite number of rows and which have in left upper corner a matrix of determinant 0, and we have here SL0, and we can look at this picture in the following ways. That here we have a scalar matrices, here we have direct product, of course, and here we have identity matrix. And when we look at this situation, we look at the following square, which is most interesting. We know here we have GL0 times scalar matrices. Here we have SL0, and here we have scalar matrices times SL0. And the situation in this square is different to that in the case of the algebra. Why this is the problem? The problem is in the fact that we have here the following situation. If we look at scalar matrices, the group of scalar matrices is isomorphic to K square, and so the quotient subgroup here is isomorphic to K square. So here we have in fact a thin line of many normal subgroups of a general linear group of column-finite matrices which contain SL0. And similar situation is here. And we proved that in fact all normal subgroups of GL column-finite in general form, which contains a special linear group with 0, must contain GL0. And because here we have a quotient G scalar matrices times GL0 divided by GL0, this quotient is also isomorphic to K square, the group multiplicative group of field. So in fact, the situation reduces to the finding of all subgroups in such a group. Here you have a direct product of K star times K star. Here K star depends on the scalar matrices, and here we have something from this quotient. And what we can say about this then, situation is much difficult because in fact we have 5 parameters which can describe such a subgroup, because we must look at normal subgroup in such direct product. And Martyna Maciaszczyk, in her talk on Wednesday, she will give a sketch of the proof of this fact. So what is the conclusion of my talk? We can say that the lattice of ideals in Lie algebra GLV and the lattice of normal subgroup in GLV are very similar in part, which contains GL0 and here GL0 finitary part. Here we have a ladder, infinite ladder, usually of such with one line here. And here we have one line. So if we take, for example, a quotient algebra or a quotient subgroup, quotient group GLV by GL0, we will see that in some sense the situation is very similar. Not isomorphic, but similar in the sense of a picture. However, situation here is much complicated, and here we have different situation for ideals in the case of Lie algebra and different situation in the case of group. I think that I will finish, and I invite to a lecture to talk by Martyna, which show a situation of this interesting square and how complicated situation is in correspondence with Lie algebra.